Hello everyone. Today we're going to talk about empirical and molecular formulas. I have two definitions for empirical and molecular formula at the top of the sheet. The first thing I want to show you first is just what they look like. We are familiar with formulas that look like this: H2O2, C6H12O6. These are called molecular formulas. Molecular formulas are formulas that show the actual composition and number of atoms in a chemical formula. Molecular formulas show that there are exactly two H's or two hydrogens and two oxygens to form hydrogen peroxide. To form a molecule of glucose, we need exactly 6 carbons, 12 hydrogens, and 6 oxygens. So it represents the actual number of atoms in a chemical formula. This is in contrast or in comparison to something called the empirical formula. The empirical formula shows purely the ratio of atoms in a formula. So when we look at hydrogen peroxide, H2O2, there are 2 hydrogens and 2 oxygens in that chemical formula. But the ratio of hydrogens to oxygens is just 1 to 1. So we would write the empirical formula as just HO. Similarly, for glucose, the ratio of carbons to hydrogens to oxygens is for every 1 carbon, there are 2 hydrogens and 1 oxygen. We're basically looking at the atoms and taking the lowest common denominator of the two. And so our empirical formula would be CH2O. That's an empirical formula. Molecular formulas are the ones that we're most comfortable or most familiar with because those are the ones that we use to communicate what the structure of a compound looks like. Empirical formulas are going to be important for us now in order to predict what a molecular formula of a compound is. Today we are going to learn how to calculate an empirical formula, and from an empirical formula, how do we determine a molecular formula. Like almost every problem that we've done in chemistry so far, there are a few steps that we can follow, and if we follow these steps in this method, we should get the results every time. It is easiest for us to first calculate the empirical formula before determining molecular formula. And so we're going to do 2 examples where we calculate the empirical formula. The first thing that you need when calculating the empirical formula is you need to be given some information about the composition of this compound. You need to be either told there are this many grams of this element and this many grams of this element, or you can be told that there is 50% of this element and 50% of this element. When giving a mass percent, we are going to assume that we're talking about 100 grams of a compound. That's just going to help to keep our math a little bit easier. After we're given some information about the composition of the compound from the question, we then need to convert our masses to moles. Moles is an easier way for us to work with. Moles is something that we can use to relate mass and atoms and a bunch of chemical things together, and so we want to convert things to moles. We convert from mass to moles using molar mass, so that is our conversion factor. When we do this, typically we do not care about sig fig, or typically we adjust for sig figs. When we do this, sig figs aren't that important for us. We're going to want to keep all of our extra sig figs to ensure that we get some nice even numbers at the end. After we convert our masses to moles, we're going to divide the moles of each element by the smallest number of moles calculated in step 2. And lastly, if any of the subscripts that we get are not whole numbers, we're going to multiply all the subscripts by a small number. I don't think 3 and 4 really make sense until we look at them, so let's jump into example number 1. Example number 1 says, determine the empirical formula of vitamin C. Vitamin C has 40.9% carbon, 4.5% hydrogen, and 54.6% oxygen. To determine the empirical formula, we first have to be given either mass in grams or the percent of each element. And in this case, we're given the percent of each element. We know that we have 3 elements in this compound: carbon, hydrogen, and oxygen. So step number 1, we need to write the mass percents in grams. And all that means, because we're assuming that there's 100 grams of the compound, that we're going to write 40.9 grams of carbon, 4.5 grams of hydrogen, and 54.6 grams of oxygen. If we assume that our compound is just 100 grams, then we can easily write our percents just straight in grams. That is all you have to do for step number 1. If you were given grams, like if it said you have 4 grams of carbon, 5 grams of hydrogen, and 4 grams of oxygen, you would not need to convert anything here. That would just be step 1. For step number 2, let's change up the color here. I like this one. For step number 2, we need to convert mass to moles. And to convert mass to moles, we use the molar mass. We have 40.9 grams of carbon. From our periodic table, we know that that there's 12.1 grams of carbon for every 1 mole of carbon. Moles is our desired unit. That goes up top. Grams goes on the bottom, so it will cancel out. We'll do the same thing from hydrogen. From the periodic table, we know for every 1.01 grams of hydrogen, we have 1 mole of hydrogen. And for every 16.00 grams of oxygen, we have 1 mole of oxygen. I'm going to play out these calculations, so I'm going to solve them. And when I divide 40.9 by 12.01, I get 3.405 moles of carbon. And I'll work through the rest of them. Feel free to pause and solve these on your own, or at least check my answers. So this is what I got when I did that calculation. Step number 3 says we need to divide the moles of each element by the smallest number of moles calculated in step 2. When I look at the moles that I calculated in step 2, 3.405 is the smallest number. And so, like step number 3 says, I'm going to divide each element by this number. So I'm going to divide each element by 3.405. This is step number 3. And I am going to calculate this out and see what I get. 3.405 divided by 3.405 is just 1. For hydrogen, I get about 1.3. And for oxygen, I get about 1. These numbers right here, the 1, 1.3, 1, those represent the ratio of each of our compounds to each other. So for every 1 carbon, there's about 1.3 hydrogens and 1 oxygen. When you look at a chemical formula, we don't use fractions or decimals to represent the number of atoms. We use whole numbers. And so our last step is we're going to convert each of these subscripts to a whole number so that they can easily be written in a chemical formula. So number 4 says if any subscripts are not whole numbers, like this one right here, we need to multiply all the subscripts by a small whole number to make them whole. Our only one that's not a whole number here is that 1.3. 1.3 is essentially 1.3 is essentially 4 divided by 3. To convert 4 divided by 3, we can just multiply it by 3 to make it 4. And so now I'm going to do that right here. I'm going to multiply it by 3, and that is approximately 4. When you multiply one thing by 3, you have to multiply everything else by 3. We have to factor up everything by the same number. And so this becomes 3, and this becomes 3. If you have anything that ends in 0.5, you would multiply the whole number by 2. Anything that ends in 0.3, you multiply it by 3. Anything that ends in 0.25, You would multiply it by 4. I don't think we come up with really many things that you would multiply by 5. But I guess it would be 0.2 if you would multiply by 5. This result, the 3, 4, and the 3, these represent our subscripts in our chemical formula for each of these elements. The 3 is associated with carbon, the 4 is associated with hydrogen, and the other 3 is associated with oxygen. And so when I write my empirical formula for this compound, I'm going to write C3H4O3. And this would be my final answer. This is the empirical formula. There's a lot of steps, and there's a lot to remember, and you will have to memorize these steps. But if you follow the steps exactly, you should get the right answer every time. I'm going to jump ahead and do the second example right now. I would love, if you're feeling confident about this, for you to pause the video and try the problem on your own, and then jump back in to see how I solved it. But for those of you that want to work through another one with me, let's go ahead and do step 2, or number 2. So step 1 is to write the mass in grams or the mass percent in grams for each element. We are given 60% carbon, 4.5% hydrogen, and 35.5% oxygen. They gave us percents, so we need to write them all in grams. So step number 1, I write 60 grams, let's do 60.0 grams of carbon, 4.5 grams of hydrogen, and 35.5 grams of oxygen. Step number 2, we need to convert mass to moles for each element. These are the same elements from before, so they're going to be the same format. For every 1 mole of carbon, moles is our desired unit. That goes up top. We have 12.01 grams of carbon. These numbers come straight from the periodic table. For every 1 mole of hydrogen, we have 1.01 grams of hydrogen. And for every 1 mole of oxygen, we have 16.00 grams of oxygen. The result of each of these calculations is 5.00 moles of carbon, 4.46 moles of hydrogen, and 2.22 moles of oxygen. I don't remember if I rounded these, but whatever sig figs you get, write down as many as you get, just so that we are safe and that our subscripts end up closest to what they truly should be. Step number 3 is to figure out which of these is your smallest result, and we're going to calculate, or we're going to divide each of these by the smallest number of moles. So my smallest number of moles is 2.2, and so I'm going to divide each of these by 2.2, or 2.22. And the result of those calculations is 2.25, 2.01, and 1.00. When I look at these numbers, 2.25 is definitely not a whole number. 2.01, I will say, is close enough to 2 that we will treat that as a whole number, and 1 is a true whole number. 2.25 is not whole, and so we're going to have to multiply each of these by a whole number to make the subscripts nice and even. 2.25 is essentially the same thing as 9 over 2. Let me see. .25 is essentially the same thing as 9 over 4. And so we're going to multiply this by 4 to make it a whole number. And we have to multiply everything else by 4 to do the same. When I do that, the result is a 9, 8, 4 for my subscripts. And so the 9 is associated with carbon, the 8 is associated with hydrogen, the 4 is associated with oxygen, and I'm going to write my empirical formula as such. These two equations that we came up with, they are empirical formulas. They show us the ratio of atoms to each other. Sometimes the empirical formula is the same thing as the molecular formula, but not always. And so even though there's a ratio of 9, 8, and 4 for all the elements, we may in actuality have 18 carbons, 16 hydrogens, and 8 oxygens in a true formula of aspirin. We don't know for sure, and so that's what we're going to look at on the back page. Here, we are going to look at determining the molecular formula of a compound. A molecular formula is a multiple of the empirical formula, so it's either 2 times or 3 times or 4 times the empirical formula. To determine molecular formula, you have to know the empirical formula first. So we have to find the empirical formula first. You have to also be given some extra information. We are going to be comparing the mass of a molecular formula to the mass of the empirical formula in order to find that multiple, that factor. And to do that, you have to be given the mass of the molecular formula. Example number 3 says a compound has an empirical formula of HO and has a molar mass of 34.02 grams per mole. Determine the molecular formula of the compound. What this information tells us that our molecular formula, or our empirical formula, is HO, and our molecular formula is some multiple of this. Some multiple of HO is going to be our true molecular formula, but the ratio of atoms to each other is 1 to 1. So we've already been given the empirical formula, which is nice. We don't have to solve that. What we want to do is we need to find N. We need to figure out what is that ratio of elements to each other. What is that a relationship between molecular and empirical formula? What is that factor? To find N, we are going to take the molar mass of the molecular formula, which will always be given to you, and we're going to divide it by the molar mass of the empirical formula, which we have to find. The molar mass of the empirical formula is something that we're going to be able to calculate. The molar mass of the molecular formula should always be given to you in the equation. Sometimes they might be the same, but if they're not, then the molar mass of the empirical formula, of the molecular formula, will always be larger. So we at least know the molar mass of our molecular formula, that is 34.02 grams per mole. That's been given to us. For the empirical formula, we have to calculate it just like we would calculate all other molar masses. We have 1 hydrogen, 1 oxygen. Hydrogen has atomic mass of 0.01 grams per mole. Oxygen has atomic mass of 16.00 grams per mole. When we add them together, we get 17.01, 2 decimal points for sig figs, grams per mole. And we'll put that on our denominator here. When I divide the two, 34.02 divided by 17.01, I get 2. Sometimes this won't be a perfect whole number, but it should be in most cases. That is the factor that we're going to multiply my empirical formula by. My molecular formula equals 2 times HO. We're going to distribute this 2 just like a coefficient, and so my molecular formula is 2 hydrogens and 2 oxygens. If you are already given the empirical formula, it's really just 2 steps. Find the molecular mass, or the molar mass of the empirical formula, and then divide the molar mass of one by the other to get that factor. If you're not given the empirical formula, you need to find that first. And so example number 4, you need to find the empirical formula and then from that determine the molecular formula. Again, if you're feeling confident about this, I encourage you to pause, try to solve on your own, and then come back and check your answers with me. If not, example number 4 encapsulates everything that we've talked about so far, and so hopefully we'll be able to get the answers together. A compound contains 92.9% carbon and 7.8% hydrogen and has a molar mass of 104.16 grams per mole. We need to determine the molecular formula. So we've been given that we have 2 elements, we know their percentages, and we know the molar mass of this compound. First step is write down each of the percentages as grams. So you have 92.2% carbon, or 92.2 grams of carbon, 7.8 grams of hydrogen. Step number 2, convert mass to moles. For every 1 mole of carbon, there's 12.01 grams of carbon. For every 1 mole of hydrogen, there's 1.01 grams of hydrogen. We're going to solve this. I get 7.68 moles of carbon and 7.72 moles of hydrogen. Step number 3, divide by the smallest number of moles. The smallest number of moles is 7.68 equals 1. We'll divide this by 7.68. This is not exactly 1, but it is close enough to 1 that we will treat it as 1. These are both whole numbers, so we're not going to do step 4. We are going to say from this information that my empirical formula is C1H1. We also would write that as CH. That is my empirical formula. So we know whatever my molecular formula is, the ratio of atoms to each other is 1 to 1. In order to find my molecular formula, we need to figure out what this factor of N is. What is the ratio of empirical to molecular? We have been given the molar mass of the molecular formula. That is 104.16 grams per mole. And we need to figure out the molar mass of the empirical formula. To do that, I have 1 carbon, which is 12.01 grams per mole, 1 hydrogen, which is 1.01 grams per mole. In total, this is 13.02 grams per mole. This goes on our denominator. And when I solve this, this gives me a factor of 8. And so I'm going to distribute this 8 to my empirical formula to get C8H8. This is my molecular formula of the compound based on the information that has been given to us. So that's putting all the math of the empirical and all the math of molecular together. Last question I have for you here is a thought problem. So it says, suppose we weigh out 0.2636 grams of pure nickel metal into a crucible and heat it so that the nickel can react with the oxygen in the air. After we cool the sample of nickel oxide produced, we weigh it again and find the mass to be 0.3354 grams. Determine the empirical formula of the compound. First thing I want you to think about is what is the gain in mass due to? We notice that we start off with 0.2636 grams of pure nickel, and after the nickel reacts with oxygen, we have a mass of 0.3354 grams. Think about what is the gain in mass due to. Pause, and I'll tell the answer in a second. When we started, we had pure nickel. The nickel reacted with oxygen, and when we ended, we had nickel oxide. So that gain in mass is due to oxygen. We now don't only have pure nickel, we have oxygen in that sample as well. The last question is, how can we use this information to figure out our empirical formula? So we're not trying to do molecular, we're just trying to figure out the ratio of atoms. So just like questions 1 and 2 here. I'm going to pause and maybe work with this with somebody else around you, and I will go over the answer in a second. So we have been given, we know that 0.2636 grams is pure nickel, and we're going to assume that no nickel was lost in this reaction. To figure out our empirical formula, we first need to know what elements are we working with. In the final sample, it says it is called nickel oxide, and so we should only have nickel and oxygen as our two elements here. If we know that nickel is 2636 grams and oxygen is our left out part here, but we do know that 0.3354 grams is nickel and oxygen together, we can subtract the two to find that oxygen is 0.0718 grams. So if this is nickel and oxygen all together, this is nickel, we subtract the two to find that this is oxygen. And so we know that nickel is that many grams and oxygen is this many grams. To find out empirical formula, our first step is to just write the mass in grams. These numbers are already in grams, they were not in percentages, and so we don't have to do anything else for step 1. Step 2 is to convert mass to moles. For every 1 mole of nickel from the periodic table, we see that there's 58.69 grams of nickel. For every 1 mole of oxygen from the periodic table, we know that there's 16.00 grams of oxygen. We're going to solve this to get 0.00449 moles of nickel and 0.00448 moles of oxygen. Step number 3, what is the smallest number of moles, and divide everything by that. Our smallest number of moles is right here. We're going to divide everything by 0.00488 or 4488. 0.00448. When we do that, they're not exactly 1, but both of them are very, very close to 1. And so our ratio of the two elements to each other is just 1:1 nickel oxide. This is purely our empirical formula, which is all we had to find. It just shows you the ratio of atoms to each other. If we were given the molar mass of this nickel oxide that was produced, then we would be able to find the molecular formula. But for right now, we will end there. Thank you for watching.